Good morning, all. In the last class, we have seen the spectrum of ethyl bromide and how the multiple states arriving from the spin orientation of the protons of these CH2 groups and methylene groups. Now, we are going to study the NMR spectra of ethanol. We know the what is ethanol. That is CH3, CH2, OH. So, CH3, CH2OH. How many types of protons are there? So we know that there is three distinct uh, types of protons. Three different types of distinct protons are the CH3 proton, CH2 proton, and OH proton. Three CH3 proton, two CH2 proton, and one OH proton. So these three different protons will give three signals, and we will study the spin multiplicity of these signals. So we are going to discuss the NMR spectra of extra pure ethanol under high resolution. So as I mentioned earlier, the peaks, their number of peaks will be 3. The NMR spectra of ethanol will contain 3 lines in which a 3 proton triplet. 3 proton triplet. 3 proton means CH3. 3 proton triplet is for CH3 proton, because CH3 is situating just near to the CH2 group. So because of the presence of CH2 group, CH3 signal of the CH3 group is going to split according to the n plus 1 rule. So there is two protons in CH2. So 2 plus 1, 3. And the signal or the peak of the CH3 group will split because of the influence of CH2 protons as triplet. So a 3 proton triplet, and it occurs at a delta value 1.15 delta for methyl proton. And these triplets are arising from the due to the coupling with the methylene proton, CH2 proton. And this is the NMR spectrum of pure ethanol. So we can see three lines, three signals, and which first in this figure, look at the ultra pure ethanol under the CH3 CH2 OH is there, and instead of writing A B C, instead of representing the different CH2 different protons with the different letters, here all the protons are indicated by letter A. So please correct it as CH3 proton as A, CH2 B, OH is C. So here also in the spectra also the signals, there is difference A, B, A. So A proton is for CH3 and B is the CH2 proton and C is the OH proton. So in the spectra also you have to make some corrections. So this is the spectra of ethanol. So as you know that we have to represent a signal of reference compound, that is tetramethylsilane at a delta value 0 and CH3 proton. So 3 proton triplet, because of the presence of neighboring CH2 group, 2 plus 1, 3. 3 proton triplet will be obtained for CH3 A type proton. Next is the proton of methylene protons, CH2 proton, which is indicated by B. So it can be their signal is actually quartet of doublet, and it occurs at a delta value 3.6 delta, and these quartet of doublet is obtained by the coupling with methyl proton and hydroxyl proton, because the methylene protons are situating in the middle of the methyl proton and the hydroxyl proton. So, because of the presence of the neighboring methyl proton and OH proton, our signal or our signal of methylene proton will split as quartet of doublet, because we have to apply the rule Na plus 1 into Nx plus 1, which we have mentioned in the last class. So here let us consider the Na as CH3. So 3 plus 1, 3 plus 1 is 4, 4 into, next group is OH. Here 1 proton is there, so 1 plus 1, 2, 4 into 2, that will be an octet. So because of the presence of 3 CH3 proton, our CH2 signal, CH2 peak will be first splitted as a quartet, and then each lines is further split into a doublet. That's why we get and this doublet is obtained by the coupling with the OH proton. Only one proton is there, so 1 plus 1, 2. So each line will be split into a doublet. So quartet of doublet or octet is obtained for methylene proton, B proton, and CH2 proton is split into quartet by CH3 proton, and each part of quartet is then split into doublet by coupling with the proton of OH group. That's why we are getting a quartet of doublet. Then one more proton is there, OH proton. Then look at the neighboring group of OH. What is that? CH2 proton. So definitely the peak or the line of the OH proton is going to split into 3, because it is attached to CH2 proton. So two equivalent protons are there. So 2 plus 1, 3. So our methylene protons, our OH protons are going to split into a triplet, and so a methyl proton indicated by A is also a triplet, and also OH proton is also a triplet because of the neighboring CH2 group that is situating in between the OH and CH3 proton. But though these two signals are triplet, they can be easily distinguished from the chemical shift value, delta value, and we know that if the electron negativity of the atom increases, what happens? Electronegativity of the atom attached to the desired proton increases, definitely that chemical shift value is going to increase, or it will appear at a higher delta value. So OH proton, when compared with the CH3 proton signal, OH signal will appear at a delta value 4.8, and the 3 proton triplet, that is the signal of CH3 is can be seen on the delta value at a delta value 1.15 delta. So these are the spectra of ethanol in pure state, extra pure ethanol. Next is the these are the if some let us consider an ethanol in the presence of some acid. So NMR spectra of a 20% ethanol in CCl4 containing a small quantity of hydrochloric acid. Then the spectra is like this. Spectra will be like this. Here also as ethanol contains 3 different types of protons, here also that are indicated by letters A, B, C. The CH3 protons are represented by A, CH2 by B, and OH proton is by the letter C. And look at the spin multiplicity of the spectra of ethanol in the presence of acid. It is clear that if the it's when it's compared with the spectra of ultra pure ethanol, there is a change in the spin multiplicity of this spectra. Let us see how this changes occurs. So actually the extra pure ethanol is expected to show, or extra pure ethanol shows three signals in which 3 proton triplet and 2 proton octet and a 1 proton triplet is also there. But when in the presence of small quantity of acid, the expected CH3 triplet but the CH2 proton first the CH3 the signal of CH3 proton will remain as the same. That is, three proton triplet will be there for CH3 signal, as in the case of extra pure ethanol. But look at the spectra of or signal of OH signal, OH proton and CH2 proton. Instead of an octet for CH2 proton, here we are getting a quartet. Instead of octet, we are getting a quartet in the presence of some acid. And also the OH proton, OH signal is a singlet. It's appear to a singlet. While it is appear as a 1 proton triplet for extra pure ethanol. So mainly the signal or spin multiplicity of OH and CH2 protons are reduced. And let us see how these changes occurs. So it has been explained on the basis of the fact that in acidified ethanol there is a rapid exchange of protons between the ethanol molecule. So let us consider ethanol molecule. Ethanol can be written as C2H5OH, and that hydrogen can be represented. We are going to represent that hydrogen as Ha. So C2H5OHA. That is our ethanol molecule. And in the presence of acid, acid is proton donor, and proton Hb proton is appearing, or the acid will liberate Hb proton, and this Hb proton is going to interact with our ethanol containing the proton Ha. So C2H5OHA plus Hb, that is from acid. And because of this interaction, basically first the Hb is going to attach on the oxygen atom, electronegative oxygen atom, because there is presence of lone pair of electrons in the oxygen atom. So when H plus the hydrogen atom is attached to the ethanol molecule, situation is just like that. C2H5OHA plus Hb will give C2H5O plus HAHB. The positive sign is to indicate that the lone pair of electron is shifted towards the proton H plus. So that's why it's known as that's why the oxygen is getting a positive charge on it. Then another molecule of consider this another molecule of ethanol, that is, and the proton is indicated by Hc. So another molecule C2H5OHc plus our ethanol molecule C2H5OHAHB. And here also interaction occurs, or exchange of proton occurs between the ethanol molecule. Rapid exchange occurs. So as the exchange occurs, C2H5 OHAHC plus C2H5OHB are going to occur. Then what happens here? The HC from one ethanol molecule is exchanged with the another ethanol molecule. So we are getting C2H5OHB plus C2H5OHC. This is to indicate the rapid exchange of protons between the ethanol molecule. So this rapid exchange is known as the chemical exchange, and this exchange is catalyzed by the presence of acids, bases, as well as the impurities. Impurities that commonly occur in ethanol. So the chemical exchange, the rapid exchange of proton is catalyzed by the acid, bases, as well as the impurities present in the ethanol. So if a rapid chemical exchange exists, the OH proton may be attached to many different molecules in a given period of time. So the effect of spin orientation of the CH2 protons experienced by the OH proton is averaged to a single value. This is why a singlet is observed for hydroxyl proton. And also, so what happens? I have mentioned that rapid exchange of protons would have an occur. So let us consider the HB. Our desired ethanol contain a proton HB, but the HB is not situating at our not going to situate at our desired ethanol molecule. It will exchange with another ethanol molecule. So this exchange, rapid exchange, because of this rapid exchange, the hydroxyl the proton will not reside at a particular ethanol molecule. So it will not going to split the signal of the neighboring proton, because they are not situating at a particular proton. They are undergoing rapid exchange between different ethanol molecules. So the rapid exchange results on a chemical rapid exchange of these proton will cause a reduction in the signal, because the protons are exchanging between different ethanol molecule. So the peak due to the OH signal, OH proton, the splitting of signal, splitting of neighboring neighboring peak by OH group is not happening because of this rapid exchange of protons between the ethanol molecule. So the signal of CH2 group is, instead of we are getting an octet, the CH2 proton will give a quartet, and this quartet is arising from the interaction with the CH3 proton. So the signal CH2 signal is not will not get splitted by the presence of this rapidly exchanging OH proton. So the octet, instead of octet we are getting a quartet. And also the signal of OH group is also changing, because the proton, we know the signal of OH proton sorry, this signal of OH proton is will be splitted into a triplet because of the presence of 2 CH2 proton. But because of this rapid exchange, the CH2 molecule, CH2 protons are will not be able to split the signal of OH proton, because it will not going to reside at a particular ethanol. The rapid exchange occurs. So the signal of OH proton will not undergo splitting by the neighboring proton. So instead of getting a triplet, we are getting a singlet. We are obtaining a singlet for OH proton in the case of an acidified ethanol, acidified or basic, or in the presence of some impurities. We are getting the peak of OH group as singlet. And this rapid chemical exchange causes actually the spin decoupling. We have seen the rapid exchange of proton between the ethanol molecule is occurring, and this rapid chemical exchange actually causes spin decoupling. That means their signals are, or spin multiplicity is reducing because of the this rapid chemical exchange. And it is only in acid free or base free and impurity free ethanol that has the residence time of a particular proton on a particular oxygen, and this residence time is sufficiently long for the coupling to be observed between the OH and CH2 protons. So such rapid proton exchange is found in carboxylic acids, phenols, amines, diols, etc. too. So this is the spectra of explanation for the spectra of ethanol. It's very important. So you have to write this spectra of ethanol as a question for your assignment. You have to submit this spectra of ethanol, pure spectra of ethanol, spectra of ultra pure ethanol, and also the ethanol containing some acids. So these are the two questions for your assignment. Next, we are going to study an important topic, coupling constant. The magnitude of separation or the distance or the spacing between the peaks in a multiplet arising from spin-spin coupling is just called the spin-spin coupling constant or the coupling constant. So actually the spin-spin coupling or spin-spin coupling constant or coupling constant is the magnitude of separation between the peaks in a multiplet. And this, we know the multiplet is arising from the spin-spin coupling. So the distance, the magnitude of separation between the peak is known as the coupling constant or spin-spin coupling constant. Actually it is denoted by the letter J, and it has a unit Hertz. So J is a measure of how strongly a nucleus is affected by the spin state of its neighbor, because the presence of the neighbor is the root cause for the spin multiplicity of a signal. So and the distance between the lines in a multiplet is known as the spin-spin coupling constant. So actually the coupling constant is the measure of how the spin states of its neighbor is going to affect the multiplicity or affect the signal of a particular desired proton. So that is J is obtained. It is determined by the effectiveness of the coupled interaction. And unlike the chemical shift, J values are independent of the applied field strength and also the operating frequency of the NMR spectrometer. We know that actually the chemical shift delta value is directly proportional to the applied field or the frequency of the radio frequency wave. So this is not just like the our chemical shift, sorry, coupling constant is not behaving like the coupling constant, sorry, chemical shift. Actually the chemical shift is depending upon the strength of the applied field B0 and the frequency of the electromagnetic radiation, while the chemical shift value J values are independent of the applied field strength B0 and also the frequency, operating frequency of the NMR spectrometer. So another important parameter is the chemical shift value, and let us consider as compound CH2Br, CHBr2, and let us consider the spin coupling between the two sets of proton. Let us say AA and XX, where A and X represents the number of protons in them, and each proton in one set is equally coupled to each proton in another set, and the sets being separated by a large chemical shift. So let us consider two sets of proton, compound containing two sets of proton. The number of protons are indicated by the small letter A and X, and each proton in one set will couple to each proton on the other set, and each sets are separated by a large chemical shift, because we know the chemical delta value is different for different types of proton. So this can be easily distinguished from the delta value. So the spacing of the protons, or sorry, spacing of peaks within one multiplet is same as that within the associated with the coupled multiplet, since the spin coupling is a reciprocal affair. So the the spacing of the peaks, or the coupling constant J value within one multiplet is same as that within the associated coupled multiplet, since spins and couplings are reciprocal. So this point will be clear when we are studying the spectra of CH2Br, CHBr2. So let us consider this compound CH2Br, CHBr2. In this compound, it's clear that two types of protons are the CH2 proton and CH proton, and the separation of peaks in the CH2 doublet. So the two proton doublet will be going to occur for CH2 because of the presence of one CH proton. Our CH2 signal will be a doublet. So a two proton doublet is for CH2, and when we are considering the CH proton, we will get one proton triplet because of the presence of two CH2 protons. And the separation of peaks in the CH2 doublet. So two protons are the two types of protons, one triplet and one doublet. Triplet is for the CH2 proton, and doublet is for the CH proton. CH2 proton is CH2 proton. The first proton will have a doublet, and CH proton will have a triplet. Here, this is the spectra, but instead of writing CH2Br, CHBr2, here it is written as CH2Br, CH2Br. So you have to write it as CH2Br, CHBr2. And the point is that in the NMR spectra of the CH2Br, CHBr2, the separation of peaks in the CH2 doublet would be exactly be the same as the separation of peaks in CH2 triplet. Or otherwise we can say that the J values will be same for this doublet and also for the triplet. And what is J value? J value, actually J value is the distance between the lines, or distance between the peaks, separation of the peaks, or distance or spacing between the peaks in a multiplet. So their values are same. So Jx is the coupling constant, or it is a way to represent the coupling between the protons A and X. So these peaks will have the same J value, or will have the same separation of peaks. The triplet and doublet is also getting a same value for the separation of peaks between them. The coupling constant of a group of the protons that split another one or one another would be identical within the experimental error. So the coupling constant J value of the group of protons that split one another, that is in the case of CH2 proton and CH proton here, that would be identical within the experimental error. So it's very useful in interpreting the NMR spectra, that if it contains several multiplet with different J values, we can assume that the J values, or the multiplets with the same J value, is the signals of particular compound, because the J value, coupling constant of the particular proton, group of protons that splits one another, will have identical or the same value. So let us consider a spectra. For example, a hypothetical spectra is shown here, and we can see four types of signals are there, four different multiplets are there. And look at the J values. The first quartet has a J value 7.5 Hertz, and the second signal, or triplet, will have a J value 5.5 Hertz, and the third proton is of the J value 7.5 Hertz, while the fourth proton is with the J value 5.5 Hertz. So two values of J is the 7.5 and 5.5. So it is clear that in the interaction scheme, it can be deduced that we can arrive at a conclusion that the peak 1, that is a quartet, and the peak 3, a triplet, is having the same J value. So the quartet is obviously associated with the peak 3. Peak 1 is obviously associated with the peak 3. That quartet is associated with the triplet because they have the identical J value, as a proton in each of the coupling groups interact to the same extent. And also comparing the J values of second and fourth, we can assume that the second proton, peak 2, is associated with the peak 4, or the triplet is associated with the triplet of peak 4. So for a system of 3 sets of protons well separated by large chemical shift, can be represented by AA, MM and XX. Since both ends sets are coupled to the middle set with different coupling constants, the J in the final multiplet will differ accordingly. So for a system, if the system containing 3 sets of protons and these 3 protons are 3 protons with 3 different chemical shift, can be represented by AAMMXX, and both n set that is AA and XX sets, there is a couple to the middle set with different coupling constant. The J values in the final multiplet with the they will differ accordingly. This is the another point. So when we are considering the case of coupling constants, as the coupling constant is the value of separation between the peaks in a multiplet, and these are rising from the spin spline coupling, the coupling constant will give clear indication that which peaks are associated or which groups are associated with each other. So if the two peaks have the same J value, it's a mention we have to think that these different peaks are connected with each other. So in the like in the case of this hypothetical spectra containing four signals, in which the two signals have the same J value and another two signals will have the same value. So we can assume that the first peak and third peak are associated with each other as they have the same J value 7.5 Hz, and the second peak and fourth point is related with each other. They are connected with each other with because they have this J value 5.5 Hz. So this is application of J value. Next is the magnetic equivalence. A magnetic nuclei having the same chemical shift, so that means same delta value and identical coupling constant is identical J value with regard to coupling with each other nuclei in the same spin system are said to be magnetically equivalent. That means if the nuclei is having the same chemical shift, same delta value and same J value, they are said to be magnetically equivalent. So the nuclei with the same delta value and identical J value are said to be magnetically equivalent. In other words, magnetically equivalent nuclei are chemically equivalent and they will couple identically with any other nuclei in the same spin system. So they are chemically equivalent protons and they will couple identically with any other nuclei in the same spin system. Let us consider an ethyl system, CH3CH2. The methyl proton, CH3 proton, all have the same chemical shift value, and the J value for the coupling of any these protons with any of the methylene proton is the same. So let us consider the methyl system, CH3 CH2 proton. Two types of protons are the CH3 proton and CH2 proton. So the CH3 proton, 3 CH3 protons, all these protons have the same delta value and the J value for these protons is the same. So the protons of the CH3 group are said to be magnetically equivalent. And also same is the situation of the methylene proton, 2 methylene proton. Two methylene proton will have the same chemical shift value, delta value, and the J value of these two protons are also the same. So the methylene protons are magnetically equivalent. Also the methyl protons are also magnetically equivalent protons. And the coupling between the magnetically equivalent nuclei can be ignored since they do not result in the observable spin-spin splitting and thus do not affect the spectra. Thus, in the case of ethyl group, we can ignore any coupling between the methyl proton themselves. So, or also that between the two methylene protons. So, we consider only the coupling between methyl proton and methylene proton. In short, magnetically equivalent nuclei do not split, not going to split each other, and they give a singlet in an NMR spectra. So this is about the magnetic equivalence. So the next question for your assignment is the magnetic equivalent. What is magnetically equivalent protons? So if you are considering the case of methylene ethyl system, two types of magnetically equivalent group protons are there, methylene proton and methyl proton, and the magnetically equivalent protons will not give any observable spin-spin splitting, or the peaks we can because the coupling between the methyl proton, three methyl proton, we can ignore them because they will have the same delta value and J value. So the coupling between the methyl and the methylene proton can be ignored. So only the coupling is between the two methylene proton and the methyl proton. So we can assume, or we can reach in a conclusion that magnetically equivalent nuclei do not split each other, and they will give a single signal. And let us study some spectra of simple organic compound. And we are going to study the first order spectra. And actually, the first order spectra are those in which the chemical shift difference between the interacting groups of the nuclei is large with respect to their coupling constant J. And these are in fact the spectra that can be interpreted using the n+1 rule or the simple graphical analysis. So we can assume that actually the first order spectra is a simple spectra. And let us study the acetone. First we are going to study some aliphatic system. We have seen the NMR spectra of ethyl bromide and ethanol, two aliphatic systems, and the observed signals, their relative position, and the multiplicity in the NMR spectra. For some aliphatic compounds will be considered. And the diagram shown merely illustrates the general nature of the expected spectra for the compounds, and the exact chemical shift of these protons will depend upon the various factors like the concentration of the solution, temperature, and degree of hydrogen bonding, etc. So we are going to draw some expected spectra. First, let us study the acetone. Acetone is also known as propanone because there is three carbon atoms. So the word root is prop, and it is an ketone. So that's why its name is ending with on, O-N-E. So propanone or acetone. CH3, C double bond O, CH3. How many protons, how many different types of protons are there? Only one, we know, only one set of proton. One is there. One type of proton is there. That means the CH3 proton, only the CH3 protons. That means the two CH3 protons are situating in the same situation or same surrounding. So these two, though they contain two CH3 group, these two CH3 groups are same. So only one type of proton is present here. As the both two protons, two methyl groups have the same surrounding. So only one signal will be obtained because the 6 protons are equivalent. We are getting a 6 proton singlet, a single unsplit peak, because it's a single peak. It will be a single peak because there is no proton, no neighboring proton is there to cause the splitting. So a single peak will be there, unsplit peak will be there for acetone, a 6 proton singlet will occur at a delta value 2.1 ppm. This is a spectra of acetone, CH3, C double bonds O, CH3, that is acetone, and both CH3 group, methylene group can be represented by the letter A. So a 6 proton singlet, it contains 6 protons because of the presence of 6 proton, we have to draw a indents line, or the length of the line will be should be high, because we have to represent the 6 proton. So as the number of proton increases, the intensity, peak intensity also increase. We have seen that. So 6 proton singlet, and the delta value is appearing at 2.1 ppm. It is a spectra of acetone. So if the question is asked, spectra of acetone, you have to draw the two lines. That is the first reference peak at delta value 0, and singlet, and that must be of high intensity, 6 proton singlet, and a delta value, you need not to by heart the delta value, but you have to write it as you have to draw a line close to the or near to the reference line. Just draw like that. Next is the dimethyl ether. Ether can be represented by ROR, general formula ROR, dimethyl ether. So R is CH3 group, so CH3O CH3, that is the dimethyl ether. Also it can be can also called as methoxymethane, as it contains two methyl group. It can also be called as methoxymethane. Here also two CH3 group is there, and two CH3 groups are same, will give single peak, because they are chemically equivalent, because their surrounding is similar. So we are going to get a single line, unsplit peak in the spectra. 6 proton singlet is also there for the dimethyl ether. And what is the difference between the acetone and dimethyl ether? Here in both case a 6 proton singlet is obtained. But look at the delta value. Which one will have the higher delta value? In the acetone, CH3, C double bond O, CH3. But in the case of ether, CH3O, CH3. So the in the ether, the proton is attached to the carbon is very close to a electronegative atom, oxygen, rather than carbonyl group C double bond O. So because of the presence of electronegative oxygen atom, delta value of the ether will be high. So the peak is appearing at a delta value 3.2 ppm in the case of dimethyl ether. And this shows that all the 6 protons of 2 CH3 groups of dimethyl ether have the identical chemical environment and hence show the same chemical shift. In other words, they are chemically equivalent and thereby they will absorb at the same applied field, because these 6 protons of the 2 methyl groups are chemically equivalent. Also they will absorb at the same applied field or same delta value. And as the 2 methyl groups, CH3 groups, lie on either side of the ether linkage, there is no possibility for spin-spin splitting because they are not close to each other. So their presence, these protons are these protons will not cause the splitting of protons of other CH3 group, because there is these are connected through an oxygen atom. So close proximity is not there. That's why there is no possibility for spin-spin coupling, spin-spin splitting between these two methyl group. So we are getting, as a result of this absence, we are getting a 6 proton singlet in the spectrum, and this will appear at a delta value 3.2 ppm. That's all for today's class. Have a nice day. Thank you.